Hello, welcome. My name is Abdullah Al Jamashki. In this presentation we're prepared for Dr. Faiza course, and it discuss our research paper that we made, which is an overview of the strategic prompting framework and a structural approach to large language models driven software development. An overview of the strategic prompting framework. The research paper explained how large language models can be used more effectively during software development. The main idea is that reliable results do not come from one perfect prompt, they come from structured workflow. A developer must define the task clearly, provide the correct text, use tools to check the output, correct problems based on real evidence, and stop when the requirements are met. The paper introduces a framework called struct code. This framework combines findings from research on prompt engineering, code generation, repository level tasks, debugging, software agents, token efficiency, and security. It is not a new algorithm that has been tested independently. It is practical summary of existing research. The framework is designed to help beginners, student developers, and teams use AI tools in a controlled way. The goal is to make assisted coding more accurate, easier to review, less expensive, and safer for real software development tasks. The need for clear guidance. The large A large language models can write code, explain errors, generate tests, and suggest improvements. However, their output is not always reliable. Problems often appear when the request is vague, when too much context is provided, or when important information is missing. A model may generate code that looks correct but doesn't fully solve the required task. It may also keep revising the code without making useful progress. The paper explains that the developer must define the goal before asking for implementation. The request should explain what must change, with what should remain unchanged, and how success will be measured. This prevents the model from optimizing the wrong part of the code. It also creates a clear stopping point. Without a clear objective, the model may produce unnecessary rewrites or introduce a new errors. The main lesson is not that AI coding tools need direction. The quality of the result depends not only on the ability of the model, but also on the structure of the development process. Structured coding prompt. The paper explains that useful coding prompt should work like a focused engineering brief. A good prompt is not simply a long instruction. It must contain the information that helps the model understand the task. The developer should state the goal, the programming language, the expected inputs and outputs, the important constraint, the relevant code sections, and the test that defines success. For example, a weak prompt may ask the model to improve a function. A strong prompt explains the required behavior, the function interface, the edge cases, and the expected output. This reduces uncertainty and makes the result easier to test. Examples should only be included when they remove confusion. Too many examples can create noise and waste token. The same rule applies to explanations. A prompt should not contain extra detail that doesn't affect the answer. The paper argue that the best prompt is not always the longest one. It is the prompt that makes the task clear, stable, and easy to stop. Providing targeted context. The paper argue that sending the entire repository to the model is usually not a good approach. Large code dumps waste tokens and may hide the most important information. The model should receive targeted context. Start with the function or file that needs to be changed. Then include the nearest related types, direct the dependencies, the exact error message, and the failing test. Additional files should only be added when a real information gap is identified. The paper describes this as a controlled retrieval process. The first layer is the task graph, the second layer is the local code, the third layer is evidence, such as test failure or task trace. The fourth layer is direct dependencies and related tests. Wider repository context should only be added when the task cannot be solved when the earlier layers. The goal is not to provide the smallest possible amount of context. The goal is to provide the smallest complete set of information needed to solve the specific problem correctly. The struct code framework. The struct code framework contains 6 steps. The first step is specifically the developer states the goal, interface, constraints, environment, and acceptance states. The second step is trim. The developer select only the files, symbols, error messages, that are and tests that are relevant. The third step is reason. A short plan is required when the task is complex, risky, or spread across several files. The fourth step is use tools. The code should be compiled, tested, formatted, and checked with static analysis tools. The fifth step is correct. Any repair should be based on an observed failure, such as a test result or an error message. The final step is terminate. The process should stop when the acceptance test pass or when the repair debugged has been reached. These steps are not always followed in a full loop. A small task may require only a few steps. A difficult task may return to an earlier step when a new evidence shows that more context or planning is necessary. Verification strategies. The paper states that generated code must be verified because correct looking code may still contain hidden problems. Unit testing is the first verification method. It checks whether individual functions behave as expected. The second method is compilation and static analysis. These tools can detect syntax error, type problems, dependency issues, and some unsafe patterns automatically. The third method is formatting and code quality. Checking formatting tools do not prove that the logic is correct, but they improve readability and make the patch easier to review and maintain. The fourth method is a human review, and a human reviewer must examine the logic architecture, edge cases, and important assumptions. The paper gives priority to real evidence. A failing test provides more useful information than asking the method to inspect the code again. A real stack trace is more useful than a guess about the cause of an error. Verification changes AI-assisted coding from a text-generated degeneration activity into controlled software development workflow based on measurable results. Optimizing token consumption. The paper treats token efficiency as a part of software quality. Token efficiency doesn't mean using the shortest possible prompt. A prompt can be too short and leave out necessary facts. The goal is to use tokens only for information that changes the answer. One effective method is requesting a patch or diff instead of asking the model to rewrite the entire file. Another method is limiting the number of repair rounds. Two or three focused rounds are often enough. If the same error continues to appear, the next step should be retrieving missing context, reporting the blocker, or requesting human review. The paper also recommends reducing repeated conversation history. During debugging, the model should receive the latest error, the latest patch, and the relevant code region. It should not receive the full repository or the full conversation unless they are required. The repair process must stop when the acceptance test pass. Continuing after success increases cost and many introduce unnecessary changes or new error. The strategic planning. The paper explains that planning should match the difficulty of task. A simple local edit may not need a detailed plan. Examples include fixing a small formatting issue, changing one branch of a function, or adding a basic test. In these situations, a long planning stage creates unnecessary overhead. Complex tasks require a different approach. Multi-file changes, database migration, new features with dependencies, and security-sensitive changes often benefit from a short plan before coding begins. The plan should identify the files that need inceptions, the expected edits, the order of the changes, and the tests that should be run. It should remain practical and brief. The purpose is not to generate a long explanation. The purpose is to reduce error caused by changing files in the wrong order or missing an important dependency. The paper recommends starting with the lightest workflow that can solve the problem. Additional planning, tool, or review steps should only be added when the task or the evidence uh, justifies the extra effort. Security and human review. The paper treats security as separate acceptance criticism. Functional tests are not enough because code can pass the test and still contain security weaknesses. This is especially important for authentication, authorization, payment, database changes, and sensitive data. Security requirements should be stated directly in the prompt. For example, the prompt should explain which values must not be logged, which permissions must be checked, and which secrets must never be copied into the model input. The developer should also use static analysis, dependency checks, and security-focused tests when they are relevant. However, automated tools are not sufficient on their own. A human reviewer must inspect important security assumption, authori- authent- authorization logic, logging behavior, and possible abuse cases. The reviewer should understand the application and its risk. The paper warns against treating AI-generated code as trustworthy simply because it looks professional or passes a basic test suite. Security review must be included from the beginning of the process and completed before the change is accepted. Integration, not replacement. The paper doesn't describe large language models as replacement for software developers. It describes them as tools that should be integrated into normal engineering practices. A model can generate code, explain errors, suggest tests, and propose repairs. However, the developer remains responsible for defining the requirements, selecting the correct context, reviewing the evidence, checking security, and deciding whether the code is ready to use. The framework connects AI assistance with standard software development methods. Clear goal comes from requirements engineering. Re- Relevant context come from understanding the repository. Reliable feedbacks come from compilers, test runners, formatters, and static analysis tools. Final responsibility comes from a human review. These avoid two extreme positions. The first is trusting the model without verification. The second is rejecting AI support completely. The paper supports a controlled middle position. AI should be used where it improves speed and productivity, while testing, review, and risk control remain active throughout the workflow. And last, core principle of success. The paper ends with four main principles. The first principle is to request the smallest complete change. A focused patch is easier to test, review, and maintain than a large rewrite. The second principle is to provide a minimal but complete context. The model should receive the target code, the direct dependencies, the exact errors, and the relevant test. Unrelated files should not be included by default. The third principle is to use real feedback. Compilers, test, static checks, and human review should guide the correction process. Repair should respond to observed failures instead of vague instructions to try again. The fourth principle is to keep the loop bounded. The process should stop when the acceptance criteria are satisfied. If the same failure remains after the repair limit is reached, the blocker should be reported or escalated. The overall message is that effective AI assisted coding requires a structured workflow, clear requirement, targeted context, tool-based verification, security review, and a defined stopping rule are the main conditions for reliable results. Thank you for listening and watching.